This is Abel test of type 1 or Abel theorem of convergence of improper integration of the product of function. Okay, here in the integration, the integrand is not a single function, it is the product of two functions, like Dirichelet test, right? Now the statement of the Abel test of type 1 is if fx be bounded and monotonic, may be monotonic increasing or decreasing in a t where t greater or equal to a, that is t is larger than a, and integration a to infinity gx dx is convergent. It is given that integration a to infinity gx dx is convergent. Then we have to prove that a to infinity fx gx dx is convergent. This is Abel's theorem. To prove Abel's theorem, we use two important theorems here. We already done the statement of these two theorems. This is second mean value theorem of integral calculus. This is in the form of Oester's form, and the second is Cauchy's criterion of convergence. Right? We all know these two theorems. We write already here. Now we first see that fx is bounded and monotonic. So here in the second mean value theorem also fx be monotonic, right? And gx is bounded and integrable, right? And here it is given that integration a to infinity gx dx is convergent, and since integration a to infinity gx dx is convergent, so we can write gx is integrable and bounded. Otherwise this integration is not possible and this is not convergent. Okay, so the second condition, that the gx is bounded and integrable, also satisfied. So we apply this theorem, that is second mean value theorem, for this function also. Now we apply on this expression the second mean value theorem as integration t1 to t2 fx gx dx, and this is equal to f of t1 into integration t1 to xi gx dx plus integration f of t2 into xi to t2 gx dx, where a less equal to t1 less equal to xi less equal to t2 less than infinity, or it may be. Okay, and we name this relation as 1. Also from the first condition, fx be bounded, right? Since fx be bounded, so there exists capital A greater than 0, such that mod of fx less than capital A for all x. Okay, and using this condition, we may write mod of f of t1 less a and mod of f of t2 also less a. We name these two conditions as 2. Now we use the definition of the convergence of this integration by Cauchy's criterion. What is the definition of this integration to converge by Cauchy's criterion? We know that from Cauchy's criterion, by using Cauchy's criterion, we can write there exists k a positive number greater than 0 such that for all t1 t2 greater than k, mod of integration t1 to t2 gx dx less than eta by, this is eta eta by 2a for any eta, arbitrary eta greater than 0. This is the Cauchy's criterion of convergence of this type of integration. Okay, already we write here the Cauchy's criterion. Clear? Now here k is here m, and these two relations are equivalent. We take eta by 2a in place of epsilon, where epsilon be any arbitrary number greater than 0. Here we take eta greater than 0 be arbitrary number. Now, since we know that t1 less equal to xi less equal to t2, so xi must be greater equal to k or must be greater than k. So xi satisfies this condition also, and we write mod integration t1 to xi gx dx less than eta by 2a, and mod integration xi to t2 gx dx less than eta by 2a, right? And we name these two relations together as relation number 3. Now from relation 1, by taking mod on both sides and using 2 and 3, we get mod of integration t1 to t2 fx gx dx. This is less equal to mod of f of t1, this is mod of f of t1 into mod of integration t1 to xi gx dx plus mod of f of t2 into integration xi to t2 gx dx, and we put the value from 2 and 3 here. We get the relation as less than a into eta by 2a plus a into eta by 2a. This is less than eta, right? So we get integration t1 to t2. We write here the final condition, integration t1 to t2 fx gx dx less than eta, where eta be arbitrary small number greater than 0. Now the Cauchy's criterion of convergence, this is the necessary and sufficient condition of convergence of improper integration, and which says that if integration t1 to t2 fx dx whose mod less than epsilon, where epsilon be arbitrary small number greater than 0, and for this epsilon we get m, this is greater than 0 and t1 t2 greater than m. If this condition is satisfied, we already satisfied this condition, then this type of integration a to infinity fx dx must be convergent. So by using Cauchy's criterion of convergence, we say that integration a to infinity fx gx dx is convergent. Okay, and this is complete our proof. Here we write this relation hold for all a, but we can write this is greater equal to a, because our required result for only a x greater equal to a, since the range of the integration start from a. So we can write here mod f of x less than a for all x greater equal to a in place of for all x. An important application of Abel's theorem is integration 0 to infinity e to the power minus ax into sin x by x dx, where a greater equal to 0. We use Abel's theorem in this problem. Here we let fx, this is equal to e to the power minus ax. So since a greater equal to 0, and we say that this function is bounded and monotonic also, monotonic decreasing here. So the first condition of Abel's theorem is satisfied. Okay. Now we already proved integration 0 to infinity sin x by x dx. That is integration 0 to infinity gx dx is convergent. Why convergent? Convergent. It is already proved in the class of Dirichelet test. Okay, an application. This is very important application of Dirichelet theorem or Dirichelet test. We prove this problem in this class, and you get the link of this video in the description box. So we say that this condition, that is the second condition, is also satisfied. This is convergent. So by using Abel's theorem, by using Abel test, integration a to infinity, that is 0 to infinity here, fx into gx dx, that is integration 0 to infinity fx means e to the power minus ax into sin x by x dx is convergent. Okay, this is very important application also for your exam. So the summary of the class is Abel test of type 1, the statement, the proof, and we use these two theorem to prove this theorem, and this is very important application of this theorem. Thank you for watching.